Thank you very, very much, Holger, for the kind invitation, also to the Dortmund people for having me here. Perhaps two disclaimers. So indeed, there is Leuven and Louvain. That's always a bit complicated in Belgium. When you take, so there is Leuven, which is in Flanders, and there is Louvain-la-Neuve, which means in French the New Leuven, which is another campus which was founded at the end of the 60s, beginning of the 70s. So that's the French-speaking sister university of the Catholic University of Leuven. And so the thing is that the mapping from the word Catholic University of Leuven, well, it's not a proper mapping in the sense that if you translate it to Flemish or to French, you get actually two different institutions. So that's a bit confusing. You can't just translate. And also, if you translate Leuven to English and you get Louvain, that's not the same as Louvain-la-Neuve, which is the new Leuven. So, yeah. So here at the title slide, you see my two affiliations. I used to be in UC Louvain, which is so not in Louvain, but which is in Louvain-la-Neuve. And now I am at KU Leuven. So, yeah. And what Holger talked about, so indeed, I work with Axel on the tree value analysis, also on copulas, and actually the project that you mentioned, we started it, well, I started it with Bettina Berghaus. Perhaps some of you know the name or have read the name. That was in 2017, so the first document was 8 years ago. Yeah. Well, so we are in the process of almost trying to, let's see. So I hope that a visit here will be helpful too. It's a very difficult paper. So this one is much easier. This is not about extreme value analysis. It's not about copulas. It's about another research line that I tended to be more active in the past. There was also one more confusion on the slide that has to do with my email address. So you see that I put it in bold, the first characters, because at KU Leuven, there is another Johan Segers with exactly the same name. So if you write to johan.segers@kuleuven.be, it's not me that you're writing to, but to some other person. So it's just a mess. But, okay, whatever. So I regret not having put my second and third initials on my papers from the start, because now, of course, Google Scholar is having a horrible time assigning papers to the right person. So if you haven't written your first paper yet, then my advice is if you have a second or a third middle name, is actually to use that from the start in your articles. It may save a lot of trouble later on. This is about Monte Carlo integration, which is numerical stuff, which is not at all my topic, but I got into it because of the statistical component. And so this is what makes it relevant for this particular talk. So it's together with great people from right to left, perhaps. Aigerim was a former PhD student of mine at UC Louvain, and now she's a postdoc at KU Leuven. François Portier, he used to be a postdoc at UC Louvain. Now he is a professor in Rennes in France, and actually he is the one that introduced me to the topic. There is Rémi Luc, who is a former PhD student of François, and who is now working in the private sector. And there is Émeric Dieuleveux, who joined the project later, or who joined one of the projects that I will talk about later in connection with the Wasserstein distance. So what is this talk about? It's about a series of papers, so this research line that has to do with the use of statistics to solve a very common problem, that is to calculate an integral by statistical setting. And so I will be giving a broad introduction to the topic, and then I will, depending on time, I will talk more or less about these three papers. So each chapter is kind of an independent paper. So we'll see how things work out. And what I've learned, that even if I take into account the fact that I need more time than I anticipate, that I will still need more time than after having anticipated that very thing. The problem has to do with calculating an integral, which we write as an expectation with respect to a probability measure mu. And so we try to integrate the function f over a space S, which will typically be a subset of the Euclidean space. Okay. This is, of course, a problem that arises in many situations, even in statistical context. Perhaps you'd like to integrate with respect to a posterior distribution. Perhaps you're doing maximum likelihood, but you have latent variables. So in order to calculate your likelihood, you would have to integrate over those latent variables. Completely different if you're working in finance and you'd like to calculate the price of a derivative. Typically, that's written as an expectation with respect to the risk neutral measure. So that also involves an expectation, and many more. I'm sure you've all encountered a problem at some point. You have to calculate some difficult integral for which there is no analytic solution. And of course, there is a big library tool set, whole science of doing this via deterministic methods. You've certainly heard of Gauss quadrature using the roots of certain orthogonal polynomials, all kind of quasi-Monte Carlo methods, where rather than sampling points at randomly, you choose them in a particular way. Here, this talk will be based on randomized methods, where we choose the points at which we will evaluate the function f in a random way. So often they're called particles, but for us statisticians, they're just random variables that we will sample in some way from the state space. The base method is to do this by sampling in an IID way. Now, there are more complicated ways by importance sampling or by adaptive Monte Carlo sampling, where you learn about the measure mu given the samples that you have already known, and you learn about the function f2. Here, this talk is limited to the simpler IID case. One of the papers in the stream is about the adaptive Monte Carlo case too. So I won't be talking about that. All right, so then the naive estimator, of course, for the integral will just be this sample mean. And in all its simplicity, it's an estimator or a method that has a remarkable property. And what is this remarkable property? It is that its rate of convergence is not affected by the dimension of the state space. So there is no cursive dimension. However complicated your space S may be, you may be calculating a 501 dimensional integral. It doesn't matter, because your estimator is unbiased, and the variance scales with 1 over n. So 1 over n, where n is the number of particles. Which means that, well, the variance, that's the error squared. So in order to go to the same scale as the error, you take standard deviation, you take the square root. So whatever the dimension is, you have a convergence rate of order 1 over square root n. That's, of course, fantastic. Now, the bad news is that this may be slow if calculating f is complicated. So suppose that your function f itself is a complicated thing. Perhaps there's some optimization to be done, or another integral to be computed implicitly within f. So if calculating f is expensive and you can't afford to take a big N, then as soon as the variance is not too small, this rate may still be too slow. And this is when you're looking for ways actually to accelerate the good convergence rate. Now, at first sight, this may seem impossible. I mean, if I want to estimate an expectation and I have an IID sample, how would you be able to do better than 1 over square root n? That seems like an impossible problem. But here, of course, you kind of know more. So you're pretending you're doing statistics, but of course, in theory, mu is actually known. And this extra information can indeed help you to accelerate the convergence rate. And this is what we will be doing. There exist many methods for this. And in this talk, it will be all about control. So what's the basic idea, or what's my take or our take on what control variates are? apart from the function f, you think of another function f hat, quite often a function that you will learn from the data, which you hope to be close to f, but for which calculating the integral is easy. And since an integral is a linear thing, you can subtract this approximation f hat and you can add it again. And then suppose that indeed you have chosen your model, your f hat, within a model for which calculating the integral can be done exactly and quickly. Then you could define an alternative estimator where you actually only take the Monte Carlo part of the difference f minus f hat, and then you calculate the bulk, let's say, explicitly because you have, by some magic, you have been able to find such a function. And the nice thing is that for this control variate, so here the CV does not stand for cross-validation, so it means control variates. The nice thing for this control variate estimator is that it's the variance, well, it's still rate 1 over n, but now now the factor that comes up in front is actually the variance of the difference f minus f hat, so you could say of the approximation error. And if this one is smaller than the variance of f itself, then you may actually gain. And suppose now that this f, you actually learn it from the data in such a way that it will get closer and closer to f. So you hope that f hat, depending on n now, will converge to f in some sense. And actually, this asymptotic variance here may tend to 0 too. And then indeed you will have achieved an acceleration of the convergence. So this is somehow the. And so now the remainder of the talk is about some examples where actually we're able to pull this trick and make this actually. Okay. All right. So here I will use methods from statistics to solve problems in numerical mathematics and get to efficient algorithms to compute definite integrals. Now, I'm a mathematical statistician, so I'm at least as much interested in what can you now say in terms of the theoretical guarantees. So that will have to do with the convergence rate, and hopefully we'll find a convergence rate which is faster than square root n, and perhaps even find that the rescaled estimation error or numerical error still converges to a normal distribution. So that perhaps you can even say something about the error, so you can quantify how far or how close you expect it to be. Okay. So this is asymptotics. Of course, in practice, you only have a finite n. Then also it's great to have something like the concentration inequality, where you say that with large probability, the estimation error is smaller than a certain specified error, and the specified error will depend on the sample size, will depend on the probabilistic guarantee that you want, and will, of course, also depend on properties of the function f. And the thing here to have in mind is that the nicer the function f is, the smoother it is, the faster you hope that the convergence rate will actually be. Okay, so this will also have to do with properties of the function. Okay, so this is a bit the broad program. We'll make this now more specific in a number of cases. Okay, so the first case is kind of an easy case. That's where our function f hat will come from a linear model, from a vector space. Right, so we construct our control variate for f, so the function f hat. We construct it as a linear combination of a number of basis functions. So here these basis functions are called g1 up to gm, and they're called control variates too. So the word control variate may have two meanings. Either it refers to these specific functions g1, gm, which are not random, so they're fixed, you choose them yourself, or it may refer to the function f hat previously. And so now this is where you use the knowledge of mu. So this is, let's say, the extra trump or the extra joker that you can put on the table, the extra card you can put on the table to get the convergence rate acceleration. That is, you choose the functions g in such a way that you know their integral. You can do this because you actually know mu. Since you then actually know them, you can actually subtract, or you can redefine Gj by subtracting its integral, and then we suppose here for convenience that the functions Gj are centered with respect to this distribution. All right, and so this has then the trivial but extremely useful fact that if you subtract any linear combination from f, so here it is G transpose beta, this stands for a linear combination of the function Gj with coefficients, the entries of the vector beta. Whatever vector beta you choose, in theory, you're computing the same integral, right? Because each Gj has an integral equal to 0. And so then this motivates to choose now the control variate f hat, so again, this double use of this word, by a privileged linear combination of the basis functions g by a specific vector beta star. And now, since you're totally free to choose this beta star, because first identity here always holds true, it makes sense to choose this beta star in order to minimize the variance of the resulting Monte Carlo estimate. Right? So you choose the optimal beta star in a least squared sense. Well, this is actually a very old and simple idea, and it just boils down actually to project your function f in L2 on the control space, and the control space is nothing else but the linear span, so the n-dimensional vector space of functions generated by the function g1 through g. So we choose the function g also that they are linearly independent in L2, so with respect to, because otherwise you have a redundancy, and that's always also true. Okay, so this is the basic idea. Now the thing is that this beta star, of course, you don't know. Or, well, you know that to compute this beta star is at least as hard as calculating the integral of f in the first place. Since you couldn't calculate the integral of f, you can't calculate those coefficients beta star. So you'll have to do something based on the data, based on the particles that you draw. But perhaps already this is starting to ring a bell, because what we're doing here, we're modeling f, which is a kind of a response, as a linear function of predictors g. So this actually suggests that we just use ordinary least squares, linear regression, to calculate or to estimate these features. And this is indeed how you can write down the classical control variate estimator. So what you do is you consider the values of the function f in particles xi. You consider them as the yi, so as the responses in the linear regression model. And then the control functions g evaluated at those same particles as the covariates. And then you try to model the responses by a linear function of the covariates. That means that you have an intercept. Originally, it's denoted by beta 0, but here I prefer to single it out and call it alpha. So the alpha would be the intercept, and the beta, so that they would be the regression coefficients that you attach to the covariates. So if you so you try to minimize here the sum of squares, and then so what you actually do is in the space, so in the function space, this beta that comes out is actually an estimator. That's actually the ordinary least squares estimator of this vector beta star. Because I was too lazy to change the picture from the paper, so there was a bit of a notation clash here that the phi corresponds to the g in the sense. So the phi is the same. So you're projecting f, and here I of f also, that's a notation clash, so that actually stands for the integral of f. Because since we assume that the function g have expectations 0, they're orthogonal to the constant function 1, and so you should imagine in another dimension that I can't show here that there is the constant functions, but they don't show, because everything is orthogonal to this. And so you project somehow the non-constant part of f on the control space. And then here within the control space, all integrals you know exactly, because you can precisely integrate the control functions g. And so the only randomness then will come from the residual here from the orthogonal. So this is the idea. And so the nice thing is now that the intercept in this problem, that's actually the ordinary least squares test. So you have taken out the effect that you could model through the functions g. The function g cannot model the constant part. So that's then what remains, and this is then your OLS estimate. Okay. Now, so where does now the acceleration of convergence rate come from? It comes from the fact that you are now entitled to choose or to let the number of control functions grow. So here the m will grow with the sample size n. The idea is then that this space here will become bigger and bigger. And as a result, the vertical part will become smaller and smaller. So the residual variance will become smaller and smaller. So this is what will give you the acceleration of the convergence rate. Now, take care. You can't do this too much. There is, of course, something will bite you if you take m too big. That's the classical problem in regression. If you have too many covariates, then you will be doing overfitting. So you need to protect yourself against overfitting too. So the trick is now to let m tend to infinity, but not too fast. So this is what I explain here. We let the number of basis functions g tend to infinity, so that hopefully we span the whole L2 space in the limit, so that the residual variance becomes smaller and smaller. But to protect ourselves against overfitting, we also we can't let m tend to infinity too quickly. So the question is, how fast can we let m tend to infinity, such that indeed we get here this acceleration of the convergence rate? So we had the square root m, but now we have here, we multiply this by the residual standard, here by the residual standard deviation, which tends to 0 as the number of control variates g tends to infinity. So how far can we go? And so we did the whole analysis, and there will come out a criterion on the next slides. But the intuition is that m should be sufficiently small such that each individual particle, each possible x that you could sample, will not dominate the whole analysis. So it's kind of a protection against too big an influence of individual particles. And voila. And so this is the idea of the leverage function Q, which is a bit of a complicated thing. So it has to do with the variance of the control function. So it's a kind of a gram matrix, but then some quadratic form of this. But what it is, it's the population version of the leverage of a sample point X in the multiple linear regression. So you may recall, I didn't put the slides here, but in linear regression, you have the so-called the head matrix. You may recall the head matrix. And on the diagonal of the head matrix, you have the influence of each individual observation. So this is the population version of that same quantity. And so what we found out to be almost the necessary condition is that the maximal leverage of each possible individual point X that you could draw should not be too big. It should not, yeah. And this is then the rate that we, this is the rate that we find, and this implies that the number of control functions can never be larger than square root of n. So actually it should be of smaller order than square root of n. So this is somehow an absolute upper bound that we can never cross with this.
Johan, can I ask?
Yes.
So this Q of X depends on n, right? Through the dimension.
Absolutely.
But how does it depend on n? Oh,
It does not depend on n. So this is a population.
It's a population, okay.
Yeah. So this is actually, so this is a nice thing. So well, so there are two nice things. So the first nice thing is that it does not depend on the particles on the sample size. It's a fixed thing. Now the condition here depends on m, and you could also say, well, m depends on n2, so the number of functions. M will depend on the sample size too. But another nice thing is that it does not involve the integrand f. But this only involves the control functions g. So you don't need any properties of the integrand f. So you can choose yourself the control functions g and then ensure that this particular property exists. And now, if this works, so if this condition holds, then we were able to show that if you consider now the error of this ordinary least squares control variate estimator with respect to the true integral, then it's as if you used actually the optimal beta star. And so we didn't know the beta star, we estimated it through ordinary least squares, but it's as if we have used this unknown beta star. And the residual is then of a smaller order than the main term. And this main term, so what is its size? So you see here a sample average. So we have 1 over square root n. And then this sigma n is again here the square root of this minimal variance. So the minimum variance that you can achieve by writing f as a linear combination of all functions. Okay, so this is a general result, and the proof was an interesting. Yeah, it's all based on classical statistics, so not even empirical processes are needed, but it's a very fine control of random matrices and their eigenvalues and stuff. So it was really fun to do. So this is about the rate. With some more conditions, you can even have asymptotic normality, but I didn't show this here on the slide, so that you can actually divide this by the asymptotic standard deviation and then have convergence to the standard distribution. Okay. Now, I mentioned that this leverage condition is to protect yourself against overfitting in case you have too many control variates. And the natural idea is, why not find the lasso? Now, the drawback of the lasso is that it is biased, and the solution that we found for this is what we call OLS post-lasso, so it's not our own idea. That is, first you sparsify the estimated beta vector through the lasso, and then with the selected control variates, you apply the ordinary OLS estimator. Now, so that's so that works in theory, but it didn't work so well in practice, and the reason is that for typical functions f and g, there is no reason why the expansion of f with respect to the function g would be sparse. So perhaps in statistical context, you can hope for some sparsity in the beta vector. Here, typically, there is no such reason to anticipate such sparsity, and so well, it's a nice theoretical work, but I don't expect it to be so. Okay. Yeah, so this is all kind of work on the concentration inequality for this OLS method. So again, this is fun theory. I'll flash by the formula. So this is what we managed to achieve. You have the typical thing like the error is of the order 1 over square root n. So the probability at least 1 minus delta. You have the typical scaling factor square root log 1 over delta. So this comes from the quantile of a normal distribution. So the upper quantile of a normal distribution as delta becomes small, it's of this order. Tau is like a variance factor. So you could think of tau as a kind of standard deviation, even though it's a bit more complicated. And then, so the main thing, or the main interesting thing here is that the residual term, it has the L star. And the L star is not equal to the number of control variates m, but equal to the number of active control variates, so to the number of control variates for which the beta vector is non-zero. So this was some hard work, and we learned a lot about doing asymptotics, concentration inequalities and linear programming with TLS. But okay, so this is all nice in theory, but once again, I don't think it's very practical. All right, now a fun application of this linear method for the slice and Wasserstein distance. So what is the Wasserstein distance and what is the slice Wasserstein distance? So this is a crash course on optimal transport. Imagine you have two probability distributions P and Q on d-dimensional space. And we would like to measure some distance between P and Q. Now, there exist many different metrics, but now suppose that your probability distributions P and Q, that they represent two images, right? You have, and you encode these images as in a grayscale. And so you have these pixels, and then you view those images actually as probability distributions. Let's say that the grayscale is like a probability. So they're actually huge probability vectors. Now, when you want to measure the distance between two such probability distributions, two such images, it's not a good idea to compute or to compare things pixel by pixel. Suppose you have a picture of a cat and then another picture of a cat, and the cats may be quite similar, but if they're not on the same spot on the image, and if you compare things pixel by pixel, it's as if the distance would be very large. So there is, for that specific situation, or for cases when the support may change from P to Q, because that's what's happening here, there is this other notion of distance. So it starts with the notion of coupling. The coupling gamma is a joint probability distribution that has margins P and Q. So we call what the margins are. We have the left margin of gamma is P, the right margin of gamma is Q. And then the cost of a coupling, so would be, well, you take joint random vector x, y, so x according to p, y according to q, and the joint x, y is according to gamma. It would be like the expected square difference, the expected square distance from x cubed. So that's the cost of coupling. So that's a positive number. Now the distance, or the Wasserstein distance between p and q, would be the smallest such number that you can achieve. So you have two probability distributions, let's say with finite second moments. You look for the tightest way that you can couple them. So you look for a joint distribution with margins P and Q, such that the expected difference between X and Y is as small as this. So this is, of course, a square. So then when you take the square root, this is the Wasserstein distance. And so now imagine that you're doing statistical learning based on, let's say, images, perhaps via some kernel method, and you need to compute distances. And so this could be a way to compute distances between images, that's between probability distributions. Okay, so this is optimal transport. It's a very huge and respectable field, both in pure mathematics and applied mathematics, and more recently also in statistics and also in machine learning. Now, the thing is how to compute this optimal transport. So how to compute this optimal coupling. Now, it turns out that in dimension 1, this is easy to compute. So think if now we are in dimension 1, I've got random variables x and y. What's the tightest way to couple x and y? Well, the tightest way would be via a monotone function. So you look for a monotone function here, t, such that if you apply t to x, you get another random variable, y, that has the desired distribution. And so how to find this t? Well, if x would be continuous, then you apply the probability equal transform, you get a uniform random variable, and then you apply the quantile transform, and you get the random variable y with the desired distribution. And so the essential thing here is that the function t is actually a monotone function. So that's the tightest way to couple two random variables x and y, or rather their distributions. And so then it turns out that the Wasserstein distance between p and q is actually the L2 distance between their quantile functions. So you have the quantile function of p, the quantile function of q. You take your L2 distance. So this integral then would be the square of the Wasserstein distance between p and q. Again, of course, assuming that x and y have finite second. So this is the smallest quantity that you can achieve if you compute the expectation of the difference between x and y squared for all random pairs for which x and y have pre-specified distributions. But the thing to keep in mind here is the word monotone. if we are now to do this in dimension d, we seek the equivalent of a monotone function. But what's a monotone function from RD to R to RD? There are many ways in which you could try to generalize this. So you could, for instance, think of a component-wise monotone function. Or perhaps you can think of other ones. It turns out that the right way to look at monotonicity is the following. If you integrate the monotone function, monotone increasing function, then what you get is a convex function. Right? It's a convex function, that's one for which the derivative, if it exists, would be increasing. So that turns out to be the right notion in dimension D. So a function here, T, a map from RD to RD, is called cyclically monotone if it's the gradient of a convex function. I'm simplifying a bit so people in the room that know more about this, they know that actually I should be talking about the subgradient of the function phi, but I'll simplify things. So the optimal transport plan, so the one for which the coupling between x and y is tightest, is one for which you can write t as the gradient of a convex function, and then you'd be looking at for the gradient of a convex function such that this transformation has the desired distribution Q. So now you're faced with the following problem. You know P, you know Q. Now you're looking for a convex function for which the gradient is such that if you apply this gradient to x, then you get actually y, at least in distribution. And this problem turns out to lead to a complicated system of differential equations, which can be solved numerically, but which is not so fun and which is expensive to solve in higher dimensions. And if you want to do this, because this is still for the ideal case where you know P and Q, but now suppose that P and Q, you don't know them, you only have a sample, then here you are hit by the curse of dimensionality, because Wasserstein distance is all about computing distances, sorry to go back, in RD, and the bigger D is, the more difficult it is to find these distances. The distances become bigger and bigger, the rate of convergence is slower. Okay, so a solution to this is regularization. I won't be talking about this. Another solution is to reduce the problem again to a one-dimensional problem. That's the sliced Wasserstein distance. So what's a sliced Wasserstein distance? That is, you project a point on a line, here this red line, which is determined by a point on the unit sphere. This is the unit sphere, point, we have a red line, then we project x on this red line. So we transform our random vector x, we turn it again into a random variable. So this is again a random variable, so this is a linear combination of the components of x through the elements of the vector s. You do this for x and you do this for y. So the Baroque notation means that you look at the push forward of P through the dual by S, which is the distribution of the linear combination S scalar product with. And since these two quantities are just random variables, you can easily calculate the Wasserstein distance between those two random variables, because you can do this via the L2 difference of the quantum functions. The idea of the sliced Wasserstein distance is now to do this over all S on the unit sphere, and to integrate this then over here, mu would be the uniform distribution on the unit sphere. So the idea is you sample uniformly from the unit sphere. For each point sampled S, you calculate this Wasserstein distance between univariate objects, which is easy to do, and then you integrate this over the unit sphere. So this is now where the integral comes from. This is the integral that we would like to solve. So we have an integral over the unit sphere with respect to the uniform distribution. The function we'd like to integrate is the Wasserstein distance, the one-dimensional Wasserstein distance between the univariate projections of P and Q on the line determined by unit vectors. So we need now control variates. So which control variates do we take? So that was the idea of Numerics, so the first author. That is actually to use spherical harmonics. And these are the orthogonal polynomials with respect to the uniform distribution on the unit sphere. So what they are, or what's specific about this, is that on the unit sphere, of course, we have the sum of squares by definition is equal to 1. So that means that if you take a polynomial and you multiply it by this thing, you actually have the same polynomial when you restrict it to the unit sphere. So it's as if you factor out in the algebra of polynomials, as if you factor out this polynomial. And so what you get are the spherical harmonics. If you express them in dimension d equal to 2, so then each point is just a cosine and a sine of an angle, and actually what you get is the classical Fourier basis. So this is like a generalization of the Fourier basis to a dimension. And so we take, as control variates, we take those spherical harmonics up to a certain degree, and then we define the estimator, let's say, of this slice Wasserstein distance through the framework in the previous paper. So by the ordinary least squares estimator, by modeling the one-dimensional Wasserstein distances as a polynomial, so as a linear combination of these spherical harmonics up to a certain. And this turns out to work marvelously well. So we achieve indeed an acceleration of the convergence rate. So here the acceleration that we obtain is equal to 1 over the degree, so the maximal degree of the polynomials. And the leverage condition actually puts an upper bound on the degree that we can take. The upper bound depends on the dimension d, because the bigger the dimension d, the more polynomials, of course, you need in order to exhaust them all up to a certain degree. And we get this because the integrand here, the integrand f that we have, is always a Lipschitz function, because if you change the angle s, you change the distributions of the projections only by so much, and so the consequence is that the function here, that is distance, also time distance between univariate projections, depends in a Lipschitz way on the angle s. There's a bunch of open problems here. So we suspect that if P and Q have densities, then this function here that you're approximating will be smooth. And the smoother it is, the easier it will be to approximate it by polynomials. And so the quicker the acceleration will think of when you approximate a one-dimensional periodic function by a Fourier basis, then the smoother that function is, the better the approximation is. I have some picture here. So here we took, for the measures P and Q, we took measures with two atoms. So they are very discrete. So this is about the worst thing that can happen, about the most difficult situation. And you see that the function f that we're calculating, that's the function in black. You see it's a periodic function, but it has these kinks here, right? So these kinks, they occur at angles where you hit the atoms. That's where the function is no longer smooth. And the functions in color, they represent the polynomials, so the polynomial approximations. And you see how the polynomial approximations are trying to get to these kinks. But of course, yeah. So this is a difficult situation, and you need a fairly large degree in order to match this kink by the full polynomials. If, however, you do the same thing with two smooth distributions, then even for low dimensions, the error is so small that it's lower than the machine accuracy, so that it's really quick. Yeah, but we haven't understood yet exactly how this works, and the bottleneck is to understand how smooth this function f is if you know that P and Q have a certain amount of smoothness. For instance, if they have densities, and these densities are also smooth. All right. As expected, I have little time left, so I'll limit myself here to the basic idea. So another part of control variates. And this has to do with a completely different method. This has to do with the non-parametric method, where we use the idea of nearest neighbors. So I go back to the introduction. We look for a function f hat of which we can calculate the integral, and which is close to f, such that the Monte Carlo part here is much smaller than the Monte Carlo part that we would only be using. So far, we have constructed f using a linear model. Now, in this project, we try to build f hat here by using a nearest neighbor estimate based on the observed sample. That's the basic idea. Now, the problem here is that if you want to approximate fxi by a nearest neighbor within the sample, that's not going to be very helpful because the nearest neighbor of xi in the sample is xi itself. So then what we do instead is we use a leave one out method. So we look for the nearest neighbor of xi within the sample, but without xi itself. We use leave one out nearest neighbors. So in machine learning, you've probably heard of k nearest neighbors. K nearest neighbors is useful when you observe the response only with noise, right? Because then then you want to average out over a number of neighbors in the neighborhood. Here we don't have noise. We assume that we can calculate the integrand f exactly. So since we somehow observe the response without any noise, there is no statistical error in that respect. And so we don't need to use k nearest neighbors. We really go for the closest. Some artistic pictures that we kindly took from Wikipedia about nearest neighbors. So this would be nearest neighbors on a linear space, but you could also do, so this is the how is it called? The Villon triangulation. So so what you see here, for instance, here in this yellow pentagon. So what it represents is for this cross, the yellow pentagon that represents all points that are closer to this particular cross than to any other. So you find a partition of the plane into Voronoi cells, and then if you connect those crosses in a certain way, then you get a triangulation, which also has very nice properties. But you can this actually works in any metric space. So this would be the same idea that the Voronoi cells and the triangulation here on a sphere. Just to give you an idea. Okay, so we work here with nearest neighbors. Bit of notation. Here n hat, that corresponds to the nearest neighbor of a point in the sample. And then when you, in a point x, you evaluate f in the nearest neighbor. So that's the one nearest neighbor estimate of f at x. But again, we don't use this at the sample points itself. So there we use the leave one out strategy. And so the important thing is here. So we leave out sample point xi. We then compute the nearest neighbor, and we will do this. So we will evaluate that this function is leave one out at the sample point x. So this will be our nearest neighbor estimate. Okay, so this is how we calculate this control. Okay, and then there is all kind of interesting theory, but since I would like to leave some time for questions, go too far. So we work on a general metric space that we have, for which we assume that there is some kind of dimension. So the dimension has to do with the volume of small balls, and the volume of a ball scales with the radius. And so this power here, that's what we think of the dimension. It's not necessarily an integer number. It could be a non-integer number too. We assume that the function is continuous and a bit more than continuous, so that it's Hölder continuous. If h would be 1, then you would have a Lipschitz function, but it would be rougher than that. And then so we find indeed the convergence rate, and we see that we have an acceleration of the convergence rate, so the one observed n, acceleration by factor that depends on the sample size n, by the smoothness of f, and by the dimension here of the metric space. Okay. All right. So that was quick. I still managed to be on time. So what did I try to entertain you with in this talk? So to showcase how ideas from statistics can help in solving methods in solving problems in numerical mathematics, more specifically the calculation of integrand, that you can actually achieve acceleration of the convergence rate because you know mu, so you know a little bit more than classical statistical context that I showed you. A parametric way via a linear model and a non-parametric way via nearest neighbors. All right, thank you very much for your attention.